For the physical properties of amines, the boiling point of the amine is less than that of the alcohol. The reason why, because alcohols, they have stronger hydrogen bonding interactions than the amine, and the oxygen in the alcohol is more electronegative than that of the amine. Now, amines are involved in hydrogen bonding, but that is only restricted to primary and secondary amines only. Tertiary amines are they don't have any hydrogen bonding. So let's have an example in there. If we have a primary amine, two primary amine molecules that are next to each other, so that is an R and H. Here you go, a nitrogen, hydrogen. These are two primary amines that are next to each other. We do have a hydrogen bonding interaction because between the first amine and the second one in there, because the amine does have a hydrogen, so it is a hydrogen donor in there. So there is a hydrogen bonding interaction. Of course, that is going to increase the boiling point of the amine, but it's not going to be as high as that of the alcohol. Secondary amines, they also have hydrogen bonding interactions. So if I have two secondary amines that are next to each other, then you would easily see the hydrogen bonding interaction there. And the only reason why you do have hydrogen bonding, because as I said, like for primary and secondary amines, those they have hydrogens in there, so they are hydrogen donors. So this one has a hydrogen in there, so it can do hydrogen bonding with the second amine molecule in there, and that is the secondary amine. So that increases the boiling point of the amine. On the other hand, if you have two tertiary amines that are next to each other, so here you go, this is a tertiary amine. You notice that here the nitrogen has no hydrogens around it. This is one of the conditions of hydrogen bonding, is that your molecule needs to have a hydrogen in there, and that needs to bond with the electronegative element of the second molecule. But here I have no hydrogen bonding whatsoever. So, and this means that this will decrease the boiling point of the tertiary amines. So this is why you see tertiary amines having lower boiling points than the primary and the secondary amine. So tertiary amines, they have lower boiling points compared to secondary and the primary amines due to hydrogen bonding. Okay. Now, normally low molecular weight amines, these are gases, and we're talking about 3 carbons or less. These are gases at low temperature. They have a very, very low boiling point. And then amines that are greater or equal to 6 carbons, these are water soluble. Now, more than 6 carbons, you are increasing the number of carbons in the chain. And we know that as you increase the number of carbons in the chain, the solubility is going to decrease. But the main reason why primary and secondary amines are water soluble, less than 6 carbons, is because of hydrogen bonding. Now, for the reactions of amines, the main reaction for amines is the acid-base reaction, because we know that amines, they do have a nitrogen with 3 bonds and a lone pair. And we mentioned earlier that the lone pair is a sign of the nitrogen being basic. Basic is another word for electron rich. Okay, so amines uses the lone pairs to act as a base, and the rule always with acid-base reactions that bases take acidic hydrogens. So the role for the nitrogen here is to use its lone pairs and react with an acid and take its hydrogen. Okay, so every time you see a nitrogen with a lone pair, that is going to act as a base in a case you have an acid or an acidic hydrogen that is reacting with it. So the first reaction is the reaction of amines with water. Water here is acting as an acid. We normally explain an acid by its hydrogen or by its electron deficient group. So for us guys, an acid is gonna have a hydrogen, okay, and that hydrogen normally needs to lack electrons. Now, in order to lack electrons, as you can see, if we apply the rules for the flow of electron or the direction of polarization, I know that oxygen is more electronegative than the hydrogen. So this means that the oxygen is going to take electrons from the hydrogen, and it's going to make this hydrogen um, electron poor, okay? And we represent the electron deficiency by a positive sign. This means that this hydrogen needs electrons. By definition, an acid needs to have a hydrogen that needs electrons. And the more electrons the hydrogen needs, the more acidic it is. Now, water is a weak acid. We know that water is a neutral. It's neither acidic nor basic, but water in some reactions, either it behaves as an acid from its hydrogen or it behaves as a base from its oxygen. It's either or depending on what it is reacted with. For this reaction to happen, we need to have an acid reacting with a base, because I know that acids and bases, they react with each other. I cannot have two acids reacting with each other, and I cannot have two bases reacting with each other. So if I chose this hydrogen to be the acid part of water, then this means that this water needs to react with a base, because we know that acids react with a base. So we're going to take this hydrogen here, and we're going to say that, you know what, this hydrogen over here, because it's partial positive, this one is going to be the acidic hydrogen. And by applying the rule that bases take the acidic hydrogen, I know that the base is going to come and take that hydrogen in here. Now, for looking at the amine, where is the base in the amine? The base is always the part of the molecule that has the lone pair. So here the lone pairs are on the nitrogen. So this is why I know that this is the basic part of the amine in there. So that amine, that nitrogen, it's going to act as a base. And the base, as by definition, the base uses its lone pairs to make a bond with the hydrogen. We know that every sigma bond is two electrons. So the base is going to use its electrons to make a bond with hydrogen in there. Bases take acidic hydrogens, and if this happens, then we're going to make a new bond between the nitrogen and the hydrogen in there. Let's go ahead and draw that a new bond as a bond like this, and then a hydrogen over here. So the base is going to come and take this hydrogen and create that new bond in there. Okay, so notice the nitrogen is going to end up having 1, 2, 3, 4 groups around it. No lone pairs, so I know that my charge on the nitrogen is a positive charge. Please remember that nitrogen with 4 groups around it should have a plus charge, and we're going to call this an ammonium ion, okay? Plus, of course, whatever is left from the water. Whatever is left from the water is the OH minus, because I broke this bond between the hydrogen and the oxygen, and I added the electrons of this bond to this oxygen in there. So I'm going to end up getting the OH, and I know that when oxygen has one bond, it's a negative charge. So this is going to be an OH minus. Again, put it as a note that when oxygen has 3 lone pairs and 1 bond, okay, we've talked about these formal charge tables earlier, it is a negative charge there. So what I'm forming over here is a simple salt. This is what I am forming. A positive charge on the nitrogen, negative charge on the oxygen. The rule says that if you start with 0 charge in the reactants, your products have to be 0 charge. And here, this is an ammonium ion, so I can simply name it as an alkyl ammonium hydroxide. Okay, so that is going to be an alkyl ammonium. This is the general name for it. Ammonium and hydroxide. The negative part is always left at the end. the positive part is always named in the beginning. So you name the positive part of the ammonium and then the negative part in there. And of course, if there's any R, that is going to be an alkyl based on that R in there. So let's go ahead and have a specific example on these reactions. By the way, these reactions happen with primary, with secondary, with tertiary, because all I am targeting is a nitrogen having a lone pair. So whenever I have this case, then this means that I do have a base in there, and the rule says that the base takes the acidic hydrogen. Okay, so in all of these examples, I'm using water as a weak acid. So my water here is going to be a weak acid. And if it's a weak acid, then I'm going to choose the hydrogen of the water. The nitrogen over here is going to behave as a base. Whether it's a primary, secondary, or tertiary amine, honestly, it doesn't matter as long as you have a base reacted with the acid. Go ahead and apply the rule that bases, they take the acidic hydrogen. So I'm making a bond between this nitrogen and this hydrogen. So now the nitrogen in my product is going to have 3 hydrogens on it. Okay, so here you go. I can write it like this. I can write it as an NH3 and it's a plus a charge in there. Okay, or I can write it as a nitrogen. I already have 2 hydrogens here. I can simply make a bond with the additional hydrogen that I am adding and put a plus a charge. This is the same as that, you guys. You can write it like this, you can write it like that. It really doesn't matter. And then the leftover from the water is the OH minus. And that is going to be my hydroxide. My charges are going to be balanced, okay? So these two are the same. If I want to go ahead and name this ammonium salt, it is an ammonium salt. Why it's salt? A salt is a term that is that normally we give for a compound that has positive and negative charges. So it's like an ACl, okay? So the name for this one is going to be, I'm going to follow the same rules whenever I want to name this. I'm going to name the alkyl first, and then I'm going to put the ammonium and the hydroxide. For the alkyl part, for this molecule here, it does have 1, 2, 3, and 4 carbons. So it's going to be, yeah. So this is 4 carbons in there. So it's going to be 1, 2, 3, and 4. It's a butyl. So the name for this one is going to be butyl. And then ammonium. And then hydroxide. If it's a 3 carbons, it's a propyl. If it's 2 carbons, it's an ethyl. So it really depends on how many carbons you have. Just follow the rules in there. Another example, again, water here is behaving as a weak acid. I need to locate the acidic hydrogen. So this is going to be the acidic hydrogen. This is going to be the basic nitrogen. Please always put on the base lone pairs. Okay, so that I would know that the nitrogen from its lone pairs, this is the basic part. So the base is going to come and take that acidic hydrogen, and my product is going to be, this is going to be an NH3 now. It's a positive charge, and then I have my negative counter ion in there on the OH. It's fine if you don't want to show the lone pairs on the oxygen, it's okay, but the charges are a must. The charges are a must to show. So if I want to name this, then that is going to be a cyclohexyl. It's an ammonium, and it's a hydroxide. Okay, so it's a cyclohexyl ammonium hydroxide. That same reaction can also happen with a strong acid. Okay, now when the acid is stronger, as we said, the acid is stronger when the hydrogen is a must, when the hydrogen is connected to more electronegative element. So here, the hydrogen was connected to the oxygen. Oxygen is an electronegative element, but if I have a halogen, okay, like a chlorine, like a bromine. So if X is a chlorine, a bromine, or iodine, I know that halogen is more electronegative than the oxygen. By following the electronegativity trend on the periodic table, electronegativity increases from left to right in a period and bottom to top in a group. In there, I know that a halogen is more electronegative than an oxygen. So this means that the halogen is going to take more electrons from this hydrogen and make the hydrogen more partial positive. Okay, and this is the definition for an acidic hydrogen. So an acidic hydrogen is a hydrogen that is more partial. The more partial positive the hydrogen is, the more acidic it is. So this one is going to be a stronger acid now. And the reason why it's a stronger acid, because the hydrogen is connected to a more electronegative element. Therefore, it is more electron deficient. Okay. So therefore, it's more electron deficient in there. And because it is more electron deficient, it's going to be a stronger acid. This means that it is in desperate need of electrons. The electron is going to take it from where? It's going to take it from the base. So we have to locate where the base is. The base always have lone pairs. So there is no possibility for you to be confused. Okay, where is my base? You look at the element that has the lone pair, and this is the base. And always apply the rule that bases take acidic hydrogens. Always. Okay? So bases take acidic hydrogens in there. The product is going to be the same, but the reaction is going to be now faster because this is a strong acid, compared to the reaction here that is a bit slower because this is a weak acid. Okay? This is the difference between a strong acid and a weak acid. So it is a faster reaction. Okay. And your product is going to be the same. It's going to be an alkyl, ammonium, but instead of having a hydroxide in there, you are going to have a halide, whether it's a chlorine, a bromine, or iodine. So that is going to be an NH3 plus in there that is counterbalanced with the halogen. We know that the halogen needs to have 4 lone pairs to have a negative charge, and we're going to name this an alkyl, ammonium, and a halide. The halide can be chloride, bromide, iodide. It is based on the halogen that you are working with. Just know that an iodine or a hydrogen iodide is more acidic than a hydrogen bromide than a hydrogen chloride in there. Okay. Let's have examples in there. So HCl is a strong acid. You choose the acidic hydrogen from the acid part. You choose the basic nitrogen from the base in there. We can do either HCl, or we can do HBr, or we can do HI, guys. Whatever strong acid you can use, the reaction can happen, but the only difference is going to be in the ion, in the negative charge ion that you are going to form. Whether you use bromine, chlorine, or iodine in the acid, doesn't matter. So my product in this case is going to be my ammonium salt, and that is going to be an H3 positive in there, and that is going to be counterbalanced with the chlorine. If you use the chlorine, and the name here is going to be a cyclohexyl, it's going to be an ammonium and chloride. Okay, if I change that and use a bromine instead, then it's going to be the same thing, a cyclohexyl ammonium, but now it's going to be a bromide. So cyclohexyl ammonium bromide. And this is the same thing for the iodine. It's going to be a cyclohexyl ammonium, and then if I have an I minus, it is going to be an iodide in there. All of these are considered to be salts, And the reason why they are salts, because salt has a positive part and it does have a negative part. Okay. So far we've considered the reaction of amines with water, which is a weak acid, with HCl or HX, which is a strong acid, and with another weak acid in here. And the other weak acid is acetic acid. So acetic acid, acidic acid. We've talked about this acid before, and acetic acid is a CH3 that is connected to the carbonyl and an OH. So that is going to be my acetic acid there. Acetic acid is considered to be a weak acid. It is stronger than water, but it is weaker than HCl or HX. So that is going to be a weak acid, but it's still an acid and it does have an acidic hydrogen in there. Okay, so the reaction is going to follow the same rules. Now notice that, why did I choose this hydrogen to be acidic and not this hydrogen on the carbon? Because we mentioned something that a hydrogen is acidic whenever it's connected to an electronegative element, because the hydrogen needs to lack electrons. And the electronegative element needs to take electrons away from the hydrogen to make it lack electrons. So this is why I chose the hydrogen that is connected to the oxygen, which is more electronegative than that of the carbon. So this is my acidic hydrogen for the acetic acid. And now I'm going to go ahead and locate my basic part. And the basic part here is the one that has a lone pair. So it's the nitrogen. Same idea, same rule, that the bases are going to take the acidic hydrogen. So I'm going to end up having my ammonium ion, my alkyl ammonium ion here. It's a tertiary butyl ammonium ion that is counterbalanced with the leftover of the acetic acid. And the leftover of the acetic acid is the oxygen, the carbon double bond O, and then the CH3. Guys, please put your charges in there. So oxygen with one bond, it's a negative charge. You can either represent it like this, or you can represent it as a CH3 C, or you can COO negative. You can write it like this, or you can write, yeah, normally we write it like that. It's a CH3 COO negative in there. This is exactly the same as that, so you can represent it with whatever way you want. These are the same in there. And when we want to name these two, these are going to be called, this is again a salt, and it's going to be a tertiary butyl, and it is going to be an ammonium, and that is going to be an acetate. The acetate is the base of the acetic acid, okay? And normally the base of the acid, we've talked about it in the chapter earlier, we end the name in ATE at the end. So this is why that name is going to be an acetate. This reaction is pH dependent in there. So if I go ahead and react the base, I know that the base here has a high pH because it is a base. So its pH is going to be more than 7 here. 7 is a neutral. It's going to be more than 7 in there. So that is going to be my base. And the pH for this one is going to be higher than 7. Okay? So we're going to say that this base is going to have a high pH. When you take that base and you react it with the acid, then you're going to have an acid-base reaction. Now, that acid-base reaction is going to produce a product, and that product has an acidic part. So the pH of the solution is going to drop down because you have now an acid in here. So your product now has a low pH. So the product has a low pH in this case because your product has an acidic part. And at the same time, your product has a basic part in here. So this is why we say that this one is a pH dependent. It depends on the pH of the solution. So the general reaction here for any type of amine that is reacted with any type of acid. So the general reaction over here. So if I start by an amine, and the amine, normally, whether it's a primary, secondary, or tertiary, amines are bases. So we're assuming here, because they are bases, I am starting with a solution of a high pH. Okay, a high pH. This is why it is basic. So I'm going to react that with any acid. Any acid, I'm just going to represent it as H plus in there. So any acid, and the acid can be strong or weak. Because you saw that if the acid is strong, if the acid is weak, we're going to get exactly the same method in there, where simply the base is going to come and take that acidic hydrogen. Of course, the reaction is going to be either faster or slower depending on the type of the acid that we are working with, but the product is always going to follow the same rule. Bases take the acidic hydrogen in there. And when this happens, we are going to form the ammonium ion, okay, in that case. And that ammonium ion is going to be the acidic part of the molecule, and that acidic part of the molecule is going to end up having a low pH. That is going to be the ammonium ion. Okay, regardless what the basic part of the molecule is, the acidic molecule is going to, or the acidic part of the molecule is the one that is going to have a low pH. Now, once you make those ammonium ions in there, okay, once you make the ammonium salt, you can simply react the ammonium salt with a base, and you're still going to end up having an acid-base reaction, because those hydrogens around the nitrogen, these are acidic. These are acidic. So here you have a base. It's a strong base because it's a negative charge. That base is going to come and take any of these acidic hydrogens. So if I go ahead and write down the Lewis structure for the RNH3 plus, it's going to look like this. I know that each one of these hydrogens, okay, so each one of these hydrogens in there, these are considered to be acidic hydrogens. Why they are acidic hydrogens? Same idea in here, because they are connected to a nitrogen with a positive charge. This nitrogen is electronegative and at the same time lacks electrons. It's going to try to pull more electrons away from the hydrogen to make it more partial positive. So all of these hydrogens are going to be considered an acidic hydrogen in there. And if they are an acidic hydrogen, this means that the base can come and take any of those hydrogens. Okay. So we're going to end up having an acid-base reaction. So any of these hydrogens here are considered to be acidic. Base can take any of those. And then you have your basic part in there. And for that basic part, remember that oxygen has lone pairs. This is why the oxygen here is your base, because it is the electron-rich part. It is negative, so this one is considered to be a strong base. And the idea, again here, same idea, bases, they're going to come and take any of those acidic hydrogens in there. And if this happens, then the ammonium ion is going to lose a hydrogen. It's going to be one hydrogen less. So you're going to end up having an H2 in there with a lone pair. Plus, of course, since the base, the OH took the hydrogen, it's going to become water. And any leftover elements that are present from the NaOH, we are left over with the sodium. And from the ammonium ion, we're left over with the halogen. Those are going to group together, and you are going to form an Na plus and an X minus in there. Charges at the end needs to balance. So you're going to form salt in this case. Okay, so notice here what I did. I started with a base. I reacted it with an ammonium salt, and my product here is going to be a base. Notice here, my product is a base. So my pH of the solution at the end is going to be high because it is going to be a basic solution, because it is present in a basic medium. Okay. The nitrogen here, notice that when the base comes and takes the hydrogen, the electrons of this bond, they add to the nitrogen. And this is why I have the lone pairs. The nitrogen now changes from a positive charge to a zero charge. Let's have another example. So choose always the basic part. So that is going to be my base. And that base is going to come and take the acidic hydrogen in there. So when it does, you are going to end up forming, this is going to be the NH2. Please put your lone pairs in there. Plus you formed water. Plus you formed the over here we do have the sodium, so that is going to be the sodium, and we're left with the chlorine in there, which is NaCl. It's up to you if you want to put the charges on the sodium or the chlorine, or if you want to leave it like this. It's really up to you, but I'm going to go ahead and put the charges in there. So this is over here an example of reactions of ammonium salts that make an amine. So here it's making an amine, and in this particular example, it's making a primary amine because I am starting with an ammonium salt that has 3 hydrogens in there. If I start with an ammonium salt that has 2 hydrogens, then I'm going to make a secondary amine. So please pay attention to that. Okay, any ammonium salt that you are working with needs to have a positive part and a negative part. It doesn't matter what the negative part is, but it needs to have a positive and a negative part. So that negative part can be a halogen, it can be an OH, it can be an acetate, it really doesn't matter. But if you have a positive part and a negative part, then this is going to be considered an ammonium salt. Whenever you want to name your ammonium salt, as we said, you name it as an alkyl ammonium and then the negative charge part that you have. So let's name a couple of them over here. So you have here an isopropyl. It is ammonium. And then leave a space and it's a chloride. Now for this example over here, notice that there is no acidic hydrogen around the nitrogen. It's all carbons in there, so the nitrogen is connected to 1, 2, 3, and 4 carbons. And this is an example of a quaternary ammonium chloride. Okay, it is actually, you do have over here 4 carbons around the nitrogen. You have 4 carbons around the nitrogen, and because you have 4 carbons around the nitrogen, you have no hydrogen attached to the nitrogen. So this means that there is no way that there is a base acid reaction, because the base now cannot come and react with the nitrogen in there because there is no hydrogen to take. Okay, there's no hydrogen to take. So this is why we say that this is an example of a quaternary ammonium salt in there, and we represent the quaternary by 4 in a circle. So quaternary ammonium salts, they don't react with bases in there. They are always pH independent. They are neutral. So therefore, there is no acid base reaction, because for a base to react, the base needs to take an acidic hydrogen, and around this nitrogen there is no acidic hydrogen. See, here there was acidic hydrogen, so the base could react, but here the base cannot react with this nitrogen in there. So this is why we say there is no acid-base reaction with the quaternary ammonium salts in there. So this is why we say also that that the quaternary ammonium salts, they are pH independent. Okay, they are pH independent. This means that they are neutral. For the other type of ammonium salts, no, they are not pH independent because their product is a base. So for this one, the product is a base. So this means that the pH in the solution is high. Here it's a base, the pH is high. But for these, you cannot react them with sodium hydroxide or any base in there because there is no acidic hydrogen. So this is why these are considered to be neutral compounds. They are pH independent, meaning that they do not react with bases.